Proton. We got some great sources from basic definitions all the way up to some pretty crazy quantum stuff.
I know, it's really interesting. It's such a basic building block of the universe, the proton, but most people don't really give it a second thought. But there's a lot more to it than meets the eye.
Yeah, and we're going to start simple, like what a proton is and why it matters, and then we'll get into all the really juicy details, quarks and gluons, and even the idea of proton decay.
Yeah, and by the time we're done, you'll have a much deeper understanding of really how the universe works at the most fundamental level.
Okay, so let's start with the basics. Everyone remembers from chemistry class, right? The periodic table, all those elements, and each element has its own unique atomic number.
Right. And that atomic number, it tells you exactly how many protons are in the nucleus of an atom. So basically, it's the number of protons that determines what the element is.
Right, right. So like without protons, we wouldn't even have all the different elements.
Yeah.
It's more than just the fact that they have a positive charge and they're hanging out with the neutrons in the nucleus.
Yeah, absolutely.
And speaking of discoveries, wasn't there a big aha moment, back in the early 1900s?
Oh, yeah. Ernest Rutherford, he was doing some experiments. Think of it like smashing particles together at super high speeds. And that's when he found evidence of these positively charged particles being ejected from nitrogen atoms. And that was basically the discovery of the proton.
So it wasn't just like a theoretical idea. They saw evidence of these things.
Yeah, it revolutionized our understanding of what an atom was. Before that, we didn't really have a clear idea of the nucleus, or even that there was a structure within the atom. So it really laid the foundation for, what we know today as nuclear physics.
Okay, so protons, they're tiny, but they're super important. And, they basically determine or they shape all the different elements that make up the universe. But I'm guessing they're involved in a lot more than just that, right?
Oh, yeah, definitely. They're essential for all kinds of phenomena, like chemical reactions. Any chemical reaction you can think of. It all boils down to how atoms are interacting with each other, and the proton plays a key role in all of that.
Right, like how atoms bond together to form molecules. I guess you could say protons are kind of the unsung heroes of chemistry, right?
Pretty much, yeah. And they're even involved in the sun. Think about it. The sun is powered by nuclear fusion, which is where protons are fusing together to create helium. And in that process, they release massive amounts of energy.
So those tiny little protons are what's powering the sun. That's incredible. I think I remember reading something about protons even being used in medicine, too.
Yeah, that's right. Proton therapy. It's a type of cancer treatment that uses a beam of protons to target tumors very precisely. So it's actually less damaging to the surrounding tissue than traditional radiation therapy.
Wow, that's amazing. So we've gone from like basic chemistry to powering the sun all the way to treating cancer, all thanks to the proton.
Right. They're a pretty big deal.
Yeah, way bigger than they seem. So that's all the basic stuff, but I think we're ready to move on to like what's really going on inside these things. You mentioned that protons are actually made up of even smaller particles.
Yeah, and that's where things get a little more complicated and a lot more interesting.
Definitely interesting. I think I'm ready to go beyond Proton 101. Let's unpack this, all these quarks and gluons you were talking about.
Okay, let's do it.
Okay, so we've covered the proton basics, what they are, why they're important. But now it's time to get to the really good stuff, the stuff that makes my head spin a little bit. You mentioned that protons are made up of even smaller particles.
Yeah, we're going to be diving into particle physics here. It's definitely mind-bending, but those tiny building blocks inside the proton are called quarks.
Okay, quarks. I heard the name before, but to be honest, I don't really know what they are.
So quarks are the fundamental particles that make up, well, protons and neutrons too.
Yeah.
And there are different types of quarks, but for protons, we only need to worry about two. The up quark and the down quark.
The up quark and the down quark. Those are their actual names.
Yeah, those are the names physicists decided to use.
Okay. It sounds almost too simple.
I know, right? But yeah, you just need two up quarks and one down quark to make a proton.
2 up, 1 down makes a proton.
Got it. But what's keeping those quarks together in such a tiny space?
Well, the force that holds them together is called the strong force, and it's one of the 4 fundamental forces of the universe. So we've got gravity, we've got electromagnetism, the weak force, and then the strong force. And this one, the strong force, is the one that really dominates within the nucleus. Okay, so the strong force is the glue that binds the quarks together inside the proton. So is it like a magnetic attraction, kind of?
It's a force, but it's a little different. The strong force is actually mediated by particles called gluons. So think of gluons as like the messengers of the strong force. They're constantly zipping back and forth between the quarks, and that's what's keeping them bound together.
Gluons.quarks. It's like a whole subatomic world in there.
Yeah.
But this strong force, it must be incredibly strong, right? If it's holding together the very building blocks of matter.
Yeah, it is. And here's where things get really interesting. You might think that the mass of a proton comes mostly from the mass of the quarks, right? Because those are the ingredients that we're using.
Yeah, that makes sense.
Yeah.
Like if you're baking a cake, the weight of the cake comes from the flour and the sugar and the eggs, right?
Right. But it turns out that's not quite the whole story. Most of the proton's mass actually comes from the energy of the interactions between those quarks and gluons. Think of it like Einstein's famous equation E lumps in this way. Energy and mass, they're really two sides of the same coin.
Wait, so the mass of a proton isn't just like the stuff inside it, but it's also the energy of those particles interacting.
Exactly. The strong force is so strong that it's creating a huge amount of energy as those gluons zip around, and that energy is what contributes to the proton's mass.
So most of the mass of a proton is pure energy. It's like saying the weight of the cake comes not just from the ingredients, but also from how much you stir it. It's like a whole new way of thinking about what mass even is.
Yeah, it really challenges our everyday understanding of the world because we think of mass as just like how much stuff is there, but really it's also about the energy involved.
Wow. Okay, so we've got these quarks held together by the strong force, and the gluons are mediating that force, and the energy of all that contributes to the proton's mass. Anything else going on in there?
Oh yeah, there's more. Protons also have what we call quantum properties, things like spin and magnetic moment, and these properties play a big role in how protons behave.
Okay, quantum properties. Sounds a little complicated. What does it even mean for a proton to have spin?
So imagine a tiny little spinning top. That's kind of what spin is like for a proton. It's this intrinsic angular momentum. It's just a fundamental property of the particle, and it's always there. And this spin, combined with the fact that those quarks inside are charged, it gives the proton a magnetic moment.
So a proton acts like a tiny little magnet because of those spinning quarks inside. It's incredible how much complexity is packed into something so small.
It really is. And this is where the theory that governs quarks and gluons comes into play. It's called quantum chromodynamics, or QCD for short. And it gets pretty complex.
UCD, yeah, you mentioned that earlier. It sounds intimidating.
It can be, but it's fascinating. It's basically a quantum field theory that tries to explain how the strong force works and how it governs the behavior of quarks and gluons. And it involves some pretty strange and mind-bending concepts.
Okay, I think I'm ready for the mind-bending. What are the key ideas behind QCD? What makes it so different from the physics we learn in school?
Well, one of the key concepts is color charge. Now, this doesn't mean that quarks are literally red, green, or blue. It's just a way for physicists to visualize another type of charge, kind of like electric charge, but instead of just positive and negative, there are 3 different types.
So color charge is just a way to describe how quarks interact with each other.
Exactly. And remember those gluons? Well, they carry this color charge between the quarks, and they're constantly changing the colors of the quarks they interact with. So it's like a constant dance of color swapping, and that's what keeps everything bound together.
Wait, so the gluons are changing the color of the quarks as they're flying back and forth. That's a wild visual.
Yeah, it's pretty cool. And this constant exchange of color charge leads to something called color confinement.
Color confinement. Now I'm really curious. What is that?
Basically, it means that we never see individual quarks roaming around on their own. They're always confined within these particles, like protons and neutrons. And that's because the strong force only really works over very short distances.
So it's like they're trapped inside the proton by this color force.
Yeah. Think of it like a rubber band. The further you try to pull those quarks apart, the stronger the force pulling them back together becomes.
Oh, okay, I can kind of picture that. So that's why we've never just found a lone quark floating around somewhere. It's always stuck inside a proton or a neutron.
Exactly. And that's just one of the many bizarre and interesting things about QCD.
So we've got quarks with color charge, gluons swapping those colors, and this whole idea of confinement. It's amazing how much is happening inside a single proton. Is there anything else? Anything even weirder?
Well, there's one more thing. Some theories predict that protons might not be stable forever. They might eventually decay.
Wait, are you saying that the building blocks of matter might just poof disappear?
Yeah, it would be a major event if it happened. But don't worry, even if proton decay is real, it would take a really, really long time for it to happen. We're talking way longer than the current age of the universe.
Okay, that's a bit of a relief. But still, the idea that something as fundamental as a proton could just, like, not be stable is pretty wild. It's like the universe has this built-in expiration date, and we just don't know when it is.
Yeah, it just goes to show how much we still don't know about the universe and what makes it tick. And that brings us to how scientists actually study these tiny particles and the forces that govern them.
Right, you were talking before about smashing protons together, like at the Large Hadron Collider.
Yeah, that's one way to do it. It might seem kind of like a brute force method, but it's actually incredibly useful for probing the inner workings of the proton.
All right, so we've learned all about quarks and gluons and color charge and all that crazy stuff. But you left me hanging about those experiments at the Large Hadron Collider. You know, the ones where they're smashing protons together. Why do they even do that?
Well, it might seem a little counterintuitive, smashing things apart to see what's inside them, but those high-energy collisions, they're one of the best tools we have to really understand how the proton works and the forces that are holding it all together.
So it's not just about breaking things for the fun of it. There's actually, like, a real scientific purpose to all those collisions.
Yeah, think of it like if you had a really complicated machine and you wanted to understand how it works, one way to do that would be to take it apart and see how all the different parts interact. And that's kind of what we're doing with protons, except on a much, much smaller scale.
So instead of gears and springs, we've got quarks and gluons.
Exactly. And the Large Hadron Collider is like the ultimate tool for creating those really high-energy collisions.
Okay, so these collisions, are they, what do they call that? Deep inelastic scattering.
Yes, deep inelastic scattering. It's designed to reveal the structure of the proton and how it changes over time. It's kind of like using a really powerful microscope to look inside the proton and see how those quarks and gluons are actually behaving.
So they're not literally like seeing the inside of a proton, but they're using the results of these collisions to figure out what's going on in there.
Right. Imagine taking two snapshots, but they're incredibly detailed snapshots of all the debris that comes out of these collisions. And by analyzing the energy and the momentum of all those particles, physicists can actually reconstruct what was happening inside the proton before the collision.
It's like a giant subatomic puzzle. They're using those particle patterns to figure out the structure of the proton.